So now, this is what Lagrange's equations look like when you start to worry about rigid body motion. For the moment, let's just concentrate on Lagrange's equations in the plane. Here's the same Lagrange equation as before, same Lagrangian. Our kinetic energy is still the 1/2 mv squared, but now there is an I angular velocity squared term as well. This I term is sometimes called the moment of inertia, which can be computed as such. If you know the mass density of your rigid body, you can go and compute its moment of inertia, which is something I think you've all done in your physics class. In this class, what we're going to do is give you m1, say as the mass of rigid body 1, and we'll just tell you I1 will be the moment of inertia of rigid body 1. We're not going to have you go and compute the moments of inertia. We'll just give them to you. So let's do a simple example. Here we have a robot that has 2 degrees of freedom, an orientation degree of freedom here, and then a prismatic degree of freedom over here. Let's assume gravity is pointing down. Our first degree of freedom is associated with this rigid body, and this rigid body has m1 for its mass, I1 for its moment of inertia, and we're going to tell you that the center of mass is a distance r1 away from the center of rotation. Likewise, this second degree of freedom here, the second rigid body, its mass is going to be m1, its moment of inertia will be I2, and we're going to tell you that its center of mass is q2 away from this point of revolution here. So we're assuming this is the joint variable. So in some ways, in this example, we're being very idealized. We didn't put a minimum joint value for what q2 can be, but that's OK for this problem. Our joint variables are going to be θ1 and d2, revolute joint, prismatic joint, and then the inputs, the generalized forces that we're going to be able to apply onto the system will be a torque for the first rotational degree of freedom, and then a force for the second translational degree of freedom. So let's start working out Lagrange's equations. The velocity of the first rigid body is going to be the linear velocity of its center of mass. And that we know is the straightforward rq1 dot. It's this distance times the angular velocity. The linear velocity of the second system will have a component due to the angular velocity, but now the moment arm is going to be q2, and it's also going to have a component of velocity in the translational direction, which is thus the velocity of q2, derivative of q2. The angular velocities for both systems, both rigid bodies, are going to be the same. It's simply going to be q1 dot and q1 dot. Both of these rigid bodies spin around this center by the same amount, the first joint angle velocity. So let's go and compute the kinetic energy of the first rigid body. It has the translational part as well as the orientation part, 1/2 mv squared, 1/2 I1 omega 1 squared. Substituting in, we have for our v1 from above, we have this form, and then for our omega 1 from above, we have this form here. Again, we just gave you the inertia. You don't have to worry about computing it. The kinetic energy of the second term, once again, 1/2 mass times velocity squared, 1/2 moment of inertia times angular velocity squared. We substitute in for these terms, and voila, this is the kinetic energy of the second rigid body. I want to point out that when doing these calculations, it's really easy to make a careless mistake. So we really encourage you to go and determine the positions and the velocities of the rigid bodies first, and then compute the kinetic energies of the rigid bodies separately, and then sum them together. After that, computing the potential energy of these systems is rather straightforward. It's the mgh of the center of mass of the first rigid body. It's the mgh, the height of the second rigid body, and it takes these forms here. Note we use ag to refer to the acceleration due to gravity. So now we can substitute it into Lagrange's equations, and we have this nice long equation here. And then at this point, to hunt for the equations of motion is simply turning the crank. The first equation of motion will have this torque is equal to this term here. And then this force is equal to this expression here. Now it's worth noting that you could have used your straightforward force balances to come up with these equations of motion. However, by using Lagrange's equations in this nice methodical process, you're more likely to not have to rely on some intuition, which I think is difficult to follow, and you're more likely to not make a careless mistake. Now, when you look at these two coupled second-order differential equations, it's worth noting that we have some terms that are the second derivative of the configuration. We have some terms that are the first derivative of the configuration. In this case, it's quadratic. And then we have some other terms that are just configuration only.